First up, we've got Victor from Early Robotics. You saw earlier, and he's going to talk a little bit further.
Thank you. Take it away. Thank you. Hi, everyone. Glad to be here. So, as they said, we just come from Early Robotics, a small startup based in Spain, in the north of Spain. And about a year ago, we started creating these embedded devices that we call brains that hope to help people making robots. So we had this vision, and we still believe it, that the future of commercial robotics wouldn't be about these humanoids of hundreds of thousands or thousands of euros, but about low-cost, open, and Linux-based robots. So we created pretty much Early Brain 1. We already sold a few hundreds of those. And now we are sort of like introducing Early Brain 2, which is based on the Raspberry Pi 2. Again, for an affordable price in open source and open hardware base. Now, people have built quite a few different robots and drones over the last year with Early Brain. So we are really looking forward to what's going to happen with these brains we deliver in the following year. One thing you've seen today is Early Spider, which is this spider-like drone. Yes, it has 6 legs. We know spiders have 8 legs. We already know that. It's just a matter of cost, and also trying to bring you a robot that actually has a great price. So you can get it on Indiegogo right now for $399, and it's going to arrive to your houses or to your research labs on December, so for Christmas. Honestly, we did a lot of work to try to put it as low cost and as affordable as possible. In the booth, you can come over and you can check the instructions. We're going to release manuals on how to hack it, how to do pretty much everything. There's people in our team already creating ROS2 packages. So our aim is to really support the work that these fantastic guys at the OSRF are doing. And of course, you, who are definitely the ones that are going to define what's going to happen next in robotics. Thank you.
Thank you very much, Victor. Next up, we've got Simon from Robot Lux, and on deck we have Andreas.
Okay, have you got the video open? So
Yeah,
1 second. Directly after the slides, we go to the video.
Yeah, we will try to do this here. Okay, yeah.
Okay, so start with the slides. Thank you.
Does anyone speak? Sorry, whose laptop is it? Lower left corner? Okay, there it is. Awesome.
Microsoft.
That was completely unexpected.
Okay, thank you. So I've been CEO and CTO of a string of startups, but I'm here as a novice in the world of robotics. I'm going to give the novice's perspective. Now, I started as a developer when I was 15 years old, when I wrote a video game and sold it to Virgin. So this is me at 15 with the world's worst fashion sense, but it was great being a teenager with money. Now, I could do that because I had a home computer, which was an entry-level platform, slide, which bridged the gap between low-end, cheap electronic kits and between super expensive systems, slide. So it enabled me to start coding and then to progress quickly to writing professional software. Let's go. What is the equivalent for robotics? In robotics, we've got toys, we've got kits with simple software, and we've got super expensive robots at the top, but we're missing something that bridges the gap. I'm clear that it has to run ROS. In April, I sold my last startup and I began playing with robotics. And I found it was much harder to get started than I thought. If we could have the video up. The first thing we need ROS to install easily on cheap hardware. And it's great to see the work that Canonical and Erlay are doing in that respect. The second thing is we need a better UI. And a video that works. Can you maximize it? So what we've got here is a web-based UI which connects to ROS running on a small robot. It's web-based so that you can control it remotely, you don't have to configure IPs. The 2 blue circles are ROS nodes running on the Raspberry Pi, which is the orange block. It's publishing and subscribing to ROS topics, which are the gray circles. We can double-click on any topic, and we can dive in and we can see the messages passing in real time underneath. Some of the topics have got special views or multiple views. So for instance, the red cube could be the representation of the orientation in space of the robot. So we can see it as a cube, or we can click through, we can see the text representation, or we can see a 3D transformation. Now down the bottom, we've got the command velocity topic, which controls the robot motors. So if we dive into that, if we had a navigation stack on here, then this would animate and show the progress of the robot. But because it's also control as well as visualization, we can use the keyboard on the browser. We can generate ROS messages, send them up to the cloud, down to the robot, scoot the robot around the floor. Finally, we've got all the ROS packages installed on the Pi on the left-hand side. And what we can do, so we've got object recognition, we've got navigation stacks, everything. What we can do is we can take one of those ROS launch targets, we can drag and drop it onto the Raspberry Pi. That sends a message up to the cloud, down to the robot, launches the nodes, and off we go. So it's a way of manipulating and debugging robot architectures in real time. You can see what nodes do just by pulling stuff across. Good for spotty 15-year-olds.
Oh, that's okay. All right, so up we have Andreas, and we're talking about robot-assisted surgery with ROS. Where are you, Andreas? There we are. And coming up after that would be Andre. I believe I pronounced that right. We did. Okay, close enough. Here's your microphone. I've got a timer.
Try to open the PowerPoint slides.
I'm just about to. Yeah.
So there should be PDF and the PowerPoint.
You want
try
PowerPoint?
the PowerPoint.
All right.
So there should
Okay.
be some videos. I hope that they work.
We will see how this goes. All right, begin.
Okay. Thanks everyone for letting me give this lightning talk. So what I want to quickly talk about is robot-assisted surgery using ROS. So what we have built, next slide please, is a modular platform for robot-assisted surgery where we integrate all of the different devices you have in an OR room and you might want to have in the OR room of the future. So that goes from medical image processing, of course, a lot of different robot actuators and a lot of environmental sensors. So we have a setup with 4 Kinect 1s and now 5 Kinect 2s that are all fused together in one gigantic point cloud, which is registered to each other, where people are recognized and they get tracked, and you can realize who is around the patient at the OR table, and your robot can move aside to let the nurse go to the patient and go back to the position it was in. Next slide, please. So in reality, this looks something like this, where we have our setup. We have an OR table with different robots attached to it. And on the ceiling, you have all kinds of sensors, like marker-based tracking systems, Kinect, time-of-flight cameras with low latency, but unfortunately also very low resolution. We have a projector on the ceiling, which allows us to do augmented reality. Also, if you count RGB LEDs as augmented reality, we have that as well. Next slide, please. What are we doing with this platform? One research project I'm involved in is trying to teach a robot how to guide an endoscope during minimally invasive surgery, only based on knowledge learned from a surgeon. And what ROS allows us to do is abstract, oh, the videos are not working, I guess. What ROS allows us to do is abstract away from the different kinematics. So we can use a 7DOF KUKA robot, we can use a 3DOF medical device, we re-engineered and ROSified, and all the higher level algorithms can stay the same. Also, we can switch between the old Kinect system, the new Kinect system, the time-of-flight camera system, and all and through the interfaces we have defined, keep our system running and do not have to modify everything all of the time. Next slide, please. So if someone wants to discuss medical ROS or ROS medical, so I just made up that logo that doesn't exist officially, please come to me. And we have also built some general purpose frameworks. First of all, ARNI, the Advanced ROS Network Introspection, which decentrally acquires metadata about your communication in your network and provides it centrally where you can test whether your network is in a healthy state. And that has been very valuable for us to provide a robust system while maintaining the flexibility. Thank you.
Thank you very much. Next up, we have Andre speaking about the Shadow Robots build tools, and on deck we have Bo.
Bring your stuff up here.
Okay, thank you. Probably everyone heard about Shadow, almost most of the people heard about Shadow Robots Dexterous Hand, which you can see today at the exhibition. But I would be talking today about a tool which we are using internally. So this is a very interesting tool. So presenter before me, it was a presentation about build form. It's actually, from our perspective, it's a very terrible experience. You have to install a lot of different software servers, so like 3 services you have to install. This is for, we have developed a platform which requires only 5 minutes of your time to make continuous integration working on any of your project, which is ROS-based and Catkin-based. Yeah. So this solution, so currently you can see one of our projects, which is indicated statuses of the builds. You don't have to set up any server on your infrastructure. You just need to create one file. In our case, it's shippable YAML, or you can, or circle YAML, any of them. In more complex scenario, you need to create additional file. So, next slide, please. And during your GitHub PRs or commits, you can see the status of the build. So which can be those, can be achieved by 5 minutes of editing one text file. So our open source, yes, next slide. So here you can see upper link is currently temporarily not working, so please refer to the GitHub. This is, it has also wiki documents inside. So you can read and see the video how to do it. So 5 minutes of your time, and you will have fully continuous integration tools up and running. You can select what you want. For example, you want code style check, you can just write one word, include one module. If you want to do code coverage with one additional word as well. Unit testing, build, everything will be done like out of box. You don't need to install anything. Yeah, so it's very easy. There are a lot of documentation with enough documentation. So this is Docker based, and yeah. So if you have any questions, you can find me either here or near the stand of the Shadow Robot in the exhibition hall. Thank you very much.
All right, next up we've got Bo speaking about integrating DDS into ROS, and next up after that is Dariusz.
Okay, hello everybody. I'd like to introduce Micros DRT, a ROS C++ kernel we modified, which integrates DDS into ROS 1. Why DDS and ROS 1? As we know, ROS 2 will be based on DDS. However, according to OSIF, ROS 1 will continue to be released for a long time. Thousands of packages will still stick on ROS 1 for a while. Could they also benefit from DDS? Okay, the next. We provide an implementation named Micros DRT, which is a modified ROS 1 C++ kernel. Its main features include existing ROS applications need no modification. By just replace or recompile the ROS CPP package, the existing ROS applications can easily take advantage of the multicast and other features of DDS. And the second one is we add some extra APIs which supports time constraint in message delivery. Newly added ROS-style real-time message pub/sub APIs which can specify such as transport priority, latency budget, and other QoS parameters. And the preferred transport means can be specified. And it is interoperable with the official ROS CPP, ROS PY core in virtue of the smart protocol negotiation and selection. Okay, next. Next slide. Okay. And we also conduct some evaluation in our lab. This is the result. Because of the time limit, I will not touch the details. Basically, in terms of scalability and transport priority, it has significant advantage over the official ROSCon. And more details and examples can be found on the GitHub. And next page. Okay, another work of our team, the Micros RTT, which is a modified C++ kernel, support hard real-time message delivery in a single computer, not distributed. It's built on top of a real-time framework of Linux. It can be acquired in the official ROS package list with the name of Micros RTT. It supports both the intra-process and inter-process hard real-time message delivery. Okay, thank you.
All right, thank you very much. Next up we have Darius, and on deck we have Cyril.
Okay, I'm also talking about the ROSCon modification. And what I did is I added another transport system using shared memory. Slide, please. Okay, how does ROS do it today? You create a message, then you publish that message on the node handle, and then the ROS core is serializing that message, sending it over a loopback network, and deserializing it again, and your callback will get it. Slide, please. Okay, what if we could do it differently? What if you could cut out the network transport, the network copying, and cut out the serialization? I'm putting the pointer, because you can't really send a pointer, right? Slide, please. Well, is that even possible? Slide. Yes, we can do it. There is this new shiny KDBus kernel messaging system, which is capable of sending encapsulated memory segments. And using some really fancy boost magic, one can actually do zero copy of memory between processes. Slide, please. The way I did it, I added a transport system and encapsulated a message in anonymous files and sent this file descriptor to another subscriber. Can't go into the detail. Slide, please. And well, what works? It is zero copy. It has memory safety, unlike nodelets. It has even reference counting, which is really magic. The downsides are, well, it's not completely transparent. One can't use the standard STL vector and string anymore. One has to switch to boost and container. But this is easily done in ROS using this GenCCP message generation, so there's not much visibility to the user. And one has to create the message explicitly using something very similar to boost make shared. I call it ROS make shared. But the only really important stuff is the performance, right? I mean, the only reason to do this shared memory is in performance. Unfortunately, it turns out that TCP transport is quite performant already. So it only really makes sense to use this if you want to send messages larger than maybe 0.5 megabyte, where most people probably use nodelets today. So that's the reason I never submitted it as a pull request, because I'm not sure how much use case is there, especially now with Force 2 coming out. Anyway, the code is on GitHub, and if anyone wants to talk to me about that, I'll be happy to. Thanks.
All right, thank you very much. Cyril? Oh, this looks exciting. And on deck, we have Pablo. So this says open source Android, and that's a lot of parts. Okay. Wait, let's all hope it's still working here. All right, this is really risky here. 3-minute demo.
Okay.
Do you want me to hold the mic? I can hold the mic.
Okay. So welcome everyone. I'm Cyril Jourdan from the Robot Studio. So we partnership with Maxon Motor. So I'm going to present our project, open source Android. So next, yeah. So So what is OSA? So we mainly focus on hardware. So as you can see, like this arm. So it's like a truly compliant humanoid robot. And we also provide like a software, so everything written on ROS, like a basic communication layer, and also simulation. And we would like to share, so it's open source, so to share with other ROS community to add more software and use this. Yeah. And, next.
Yeah, I just.
Oh, sorry. So why this kind of robot? So it's a completely different approach in robotics. So it's based, as you can see, on human anatomy. So like every wire you see here corresponds to muscle in the body. So it's called like SEA, so series elastic actuators. So it can store energy in the elasticity of the system. And it's, I'd say it's opposite to industrial robots in the sense that it's very compliant and soft and elastic. So as you can see, it's much safer to use in human environment, for example. And our goal is really like to fill the gap in the robotics hardware and to have more, to provide like an open research platform for the labs in research in robotics around the world. And so this one is a prototype, and we aim to have like a fully 3D printed for the next generation. So in conclusion, if you want to know more about us, you can Google the ROS Studio. You will find all this website, YouTube. We also have a project like this, like a 3D print in hand. You can follow the tutorial to build and to add to your project. And we have also repositories and a website under construction. So you can come to see me and talk more about it after if you want. Thank you for your attention.
All right, thank you very much. Next up, we have Pablo, and on deck is Winston.
One moment.
Thank you. So, my name is Pablo Quilez. I work in Fraunhofer IPA in Stuttgart, and I'm going to introduce the outcome of the work we did in the last time, so which is the robot movement interface. So this interface is a common effort for standardize the access to the specific capabilities of the robots. What we are implementing as topics. So the idea is to access to the specific functions of the robot. For example, impedance controlling in the IWA, or just the 7 degrees of freedom. And well, the question is why a new interface? Because it's required by the industry. So, and also because a lot of people which are not experienced with ROS or even with programming need to have access to these capabilities. And in an easy way, they cannot afford to get used to gazebo or to simulations or the whole ROS controlling. So what we are providing is a format-independent message system, so the semantic is in the message, not in the format, and this allows to change the content and to make to have the flexibility and to extend the commands very easily with new functionalities. And also we can work directly with the robot, and we can change the message depending on the requirements in the real time. And also it's ROS industrial compliant. So it doesn't replace the ROS industrial interface because it's one intermediate layer. And well, we have already drivers for the IWA, UR10 and 5, and KR16. So this is what we want to share with you, and we want to publish it. So we can go to the next slide very fast. So this is the example for the IWA. So IWA requires very specific commands. So for example, this is the table. The semantic so is in the table. Format is the same, the topic. And well, this is a photo, which is one example of what we did. Well, also there are two parts in the system. The sunrise part, which is in Java, and the ROS driver. and we are connecting it with Ethernet using like a Telnet protocol, so we can go to the next one. And also we originally programmed this for internal use and for European project. And well, we are thinking and we are going to publish it in the ROS industrial repositories. And if you have any questions or so, you can direct speak with me. So thank you very much.
All right, thank you very much. Coming up, we have Winston, and on deck is Jochen.
Hello, everyone. I am Winston Garcia from ABB Corporate Research from Sweden. I would like to share with you some results that we did for the drone project based on ROS.
One moment.
Okay.
The clock's not counting, by the way, just to be sure.
There we go.
It's number 9.
right?
Number 9. Thank you. All right.
Here it is.
There we go.
Well, we can on this next one.
Done.
Well, the idea is that we get all the information on the drone, and we send this information for a laptop and we program everything on ROS. The advantage with this is that we can use a modular design. That means we define different nodes for each block, and we have one responsible for this node. And it's really easy to integrate all this information because you can see, okay, you are responsible for this node, and you need to publish this information. And in parallel, you can put another guy working in this mission and in this block, and it was really easy to integrate all this information. That's one advantage for this modular design working on ROS. Next slide.
One more, okay. So 2 slides.
Well, this slide summarizes everything. We are using this RDROM autonomy, and we program everything using C++. We mainly did 2 nodes. One of them is for the pose estimator. Mainly this node do a sensor fusion, integrating all the onboard sensor with the GPS signals. The other node is the control system. This is basically a set of PID controllers to provide the final control element to the rotors on the quadcopter. And we have this frequency of what is 100 Hertz. Next slide. This slide summarizes the pose estimation. Basically, we use a Kalman filter to do the sensor fusion. And here you can see the estimation of the position of the drone and the confidence that we have for each point. Here you can see the real 3D data with the position of the quadcopter. The next slide. Here you can see the autonomous flying, and we have implemented the control system, basically a set of PID controllers. And here you can see the blue line is the reference, and the red line is the real position of the quadcopter. And here you can see that the system compensates on wind in this east-west position. Here we have the east-west, here we have north-south. And we have some wind in this direction, and the control system are able to compensate everything. And here you can see a 3D representation of this. Finally, ROS was really, really nice platform to develop this project. It was easy to integrate the different nodes, and was really easy to work in parallel for all these things. Next slide. If you have any question, please, we can talk during the coffee break. Thank you very much for your attention.
All right, coming up, we have Jochen. On deck is a representative from Raputa Robotics.
So hi everyone, I'm Jochen, and I'm part of the Debian Robotics team, together with Leo, who's over there as well. And we are working on bringing ROS into Debian, meaning, yes, you can put the next slide already.
Oh, great.
So I think you all know this. This is the installation instructions from the ROS wiki page, how to install ROS. And you have to put in the sources list, the key, install ROS, and at the end you still have to put in the setup bash to get everything set up. and we want to change this. Next slide. So what do you think about this? You install Ubuntu or install Debian if you want to, and you do just sudo apt-get install ROS desktop full, and you have everything installed and running on your system. No setup bash, no everything else. And as well, you can use your IDE, your build tools, and whatever you like. And, back.
Back.
And as well, we want to have stable releases, like real stable releases as in Debian or Ubuntu. We want to have rolling releases, or we will have rolling releases, where you have all new upstream versions directly available in your system. And we will have support for many different packages or many different architectures directly built in, like think of ARM directly compiled for all packages. And you don't have to re-release your packages if there's a new ROS version coming up. It's all in there already. Okay, next slide. So what did we do already? We adapted everything to the file system hierarchy standard, like you have everything in user include, user lib, like normal packages, not everything into opt. We have put in SO names. This is some special thing you need for libraries. We put in default values, like the ROS master URI, it's default, like every other thing. It just magically works. And we split packages according to the Debian guidelines as well, like you have development packages and library packages, and if you don't need the development package, you just don't install it. So, if you want this, it's coming soon into Debian. It will be part of Ubuntu hopefully as well then. And if you want to see it now already, it's in the Debian wiki, or just ask us, we will be around and tell you everything. Okay, thanks.
Thank you very much. We have next up is Reputa. Yes, Reputa. And then you are after, yes.
One slide.
Excellent. This one.
Hi, my name is Kajan, and I'm with Reputa Robotics. We started last November. We are about 10 engineers full-time. We have offices in Zurich and Tokyo. So what we are excited about is connecting robots and devices to the cloud and building low-cost, lightweight, highly autonomous systems. So currently we are working with some enterprise customers, mainly from Japan, to build security and inspection systems. And one of the core components of these products is called Reputa, an open source cloud robotics platform. So those who were in ROSCon 2013 may remember that we did a demo where we did a 3D cloud-based mapping that was Stuttgart, and we mapped in the Amazon servers in Ireland. So that Reputa was kind of a prototype. It was great, but it had its limitations. So currently we are thinking of Reputa 2.0, and as a good open source project, we want to involve the community from the right beginning. So currently we are in the requirement gathering phase. So I would really appreciate your thoughts on many things, such as I would like to hear what kind of applications would you run on the cloud? What are your requirements in terms of computation, databases, connectivity? And how do you develop and deploy applications? So as a start, we can discuss on the bird of the feathers meetings. Afterwards, we'll send out a detailed description on the mailing list on how you can participate in this effort. So thank you again for the time, and thank you for organizing the awesome conference. Thanks.
Thank you.
This is Hong, by the way.
Yeah, today I'd like to give you the brief introduction of ISO TC 184 SC2 Workgroup 10, moderator for service robot, and issue a call for expert from ROS community to join Workgroup 10. This subject is different from the ROS conference subject. Yeah, the Workgroup 10 is to explore the different aspects of robot software module to develop international modular standard for service robot. The topics covers software, electrical and mechanical modularity, and safety requirements in modular robot component interoperability and finally integrated design approach. Yeah. And this slide shows the roadmap from creation to the future. Now, Workgroup 10 is developing the first standard of Part 1, general requirement of modularity for service robot. This requirement is closely related to you. And especially software part has the following contents. First, standard satisfy the following requirements, such as reusability, compatibility, interoperability, real-time service, depending on application, independence of platform and implementation. And architecture harmonize software and hardware modules, interface for hardware abstraction for hardware access, data exchange among software modules, communication among robots, and self-configuration and safety related to, depending on application. And also, this slide is the reason why I am here. ROS community, ROS is important robot middleware and has a larger developer community. So, Workgroup 10 want to involve all stakeholders, especially ROS experts, in its work. And the last is
all right, the last lightning talk is Yan.
Let's wait for the last one.
Yeah, thank you. Yeah, hello, my name is Jan Carstensen. I'm from the Real-Time Systems group of the Leibniz University in Hanover. And we've been putting some time and effort into, well, real-time ROS, yet another approach. Slide, please. Well, what is our motivation, of course? We would like to get the reliability and the predictability of a real-time system and still use the complete ROS ecosystem, use the great ROS visualization tools, and of course, quite a lot of the code base, which is actually there. What were our main design goals, and still are? I mean, this is a work in progress. We wanted to stay as close as possible to the ROS API for at least the main parts like publish and subscribe to make the migration as easy as possible, but still, of course, deliver hard real-time, publish, subscribe communication. Thank you. We've done some preliminary testing, and of course, since we're looking at real-time, we're looking at the worst case message latency in this case, and well, this shows quite promising. Of course, I mean, ROS is not developed for real-time, but still. Currently, we've done a lot of testing and are developing. The idea would be to have a finished prototype or a releasable version at the end of the year. Currently, the loop rate spin, so the basic node functionality, is completed and tested. Publishing and subscribing is working quite well. Services are currently tested. Action server and action client are a work in progress. And as you can see, TF2, a bridge between our new system and the current ROS ecosystem is scheduled. And of course, network communication. Currently, publish, subscribe, and services are only implemented for single PC. I'm very happy if some of you have some input, some suggestions, and I would very much like input on what we're currently doing. Thank you for your attention.
All right, we have a 10-second demo while I queue up the next slide here. Okay, do we have a 10-second demo? We do. Okay, look at that.